All right, so today we are trying to look at how pH and KSP are related to each other. So these are two ideas we've looked at, nothing really new here, just taking two old ideas and combining them together. So in this first problem, we have aluminum hydroxide. It's an insoluble substance. We have a KSP value there. So what we're going to do in order to find the pH is, if we want to find the pH, we either need to know the hydronium concentration, hydronium ion, or the hydroxide ion concentration. Obviously, we can get an hydroxide ion concentration from this, and we can turn that into a pH. So start this like any normal problem. We will write a dissociation equation for aluminum hydroxide. Now remember, when we do these, we always start with the substance as a solid, and then it's going to break into its ions, and those ions are aqueous. Because of that subscript of 3 for hydroxide, we will have 3 hydroxides being produced on the product side, which obviously plays a role in how we're going to go about and solve this problem. So again, we're doing just a normal KSP problem, normal ice table problem. Aluminum hydroxide is a solid, so we can not worry about it for our equilibrium. We're going to start with 0 of the aluminum ions, 0 of the hydroxide ions. Now, some of the aluminum hydroxide is going to break apart. We'll call it minus X. For every X amount of aluminum hydroxide that breaks, we'll get X amount of aluminum being produced. We'll get 3X in terms of the amount of hydroxide we're going to get. All right, so once we have our ice table filled out, we can now go on and write an equilibrium expression. So again, solids don't get included. So we're going to have aluminum ion concentration to the first power. We're going to have the hydroxide ion concentration being cubed. And we go ahead and plug in our values from our ice table, X and 3X. And again, that 3X is being cubed. And we're going to set that equal to the KSP given to us at the beginning of the problem. So just, again, careful of your math here. We're cubing both the 3 and the X, so we're going to get 27X cubed. We have X. So after doing all the right side, we get 27X to the 4th being set equal to our KSP. So we'll divide both sides by 27. And we get 1.48 times 10 to the negative 16th. Now we're going to cubed root both, or not cubed root, we're going to 4th root both sides. And so we get an X value of 1.10 times 10 to the negative 4th. Now again, our goal was to get a pH out of all this. If we look back at the ice table, our X value was simply the aluminum ion concentration. If we triple that X value, we will get the hydroxide ion concentration. And now that we know the hydroxide ion concentration, now we're just going to be using our normal acid-base equations just to finish this up here. So if we take the negative log of this quantity, that's going to get us the pOH value. And so we get a pOH of 3.48. We'll subtract from 14 to get the pH, and so we get 10.52. So again, we're just taking two old ideas and combining them together. So again, KSP and pH equation stuff. So again, there is our pH for aluminum hydroxide. In the second problem, we're just going to be going in the reverse direction. So again, our goal is to get a KSP value. So this pH, again, we can use our acid-base equations, and we can get a hydroxide ion concentration. If we know one of the ion concentrations, then we can use that to figure out, we can use the balanced equation, and we can plug in an equilibrium expression to get a K value. So we'll subtract this pH from 14, and that'll give us a pOH value of 4.13. Once we have a pOH value, on the equation sheet we have the equation that allows us to take a hydroxide concentration and get a pOH. We have a pOH, so we're going to need to undo that log function. So again, we'll multiply both sides by -1. To undo the log function, we got to 10 to the both sides. And so we end up with 10 raised to the negative 4.13 power. And so our hydroxide concentration, 7.41 times 10 to the negative fifth. So that is a molarity. All right, so again, we have the value that's going to be plugged into our ice table. Once we have that, we can get a KSP value. So treat it just like the last problem. Treat it like any normal KSP problem. We have our magnesium hydroxide. It's an insoluble substance, so we start with it as a solid. And we're going to break it into its ions. 2-to-1 ratio between the hydroxide and the magnesium. If we set up our ice table, the magnesium hydroxide is a solid, so we're not going to worry about it in our equilibrium expression. We do start with 0 of each of those ions. All right, so at this point, we do know, so again, that pH is telling us that there's hydroxide ions floating around. Now, this is after we've allowed it to break apart, so this is going to be at equilibrium. So we started with 0 amount of hydroxide. We now have 7.41 times 10 to the negative fifth. So that was our change. Because of the 2-to-1 ratio between the magnesium and the hydroxide, the magnesium amount is going to be half of the quantity that we have for the hydroxide. And so now that we have those two quantities, we now have enough information that we can get a KSP value. So again, we'll set up our equilibrium expression. Products over reactants, the reactants of solids, so we're not going to include it. The magnesium concentration is going to be multiplied by the hydroxide concentration after we square the hydroxide ion concentration. And so we get a KSP value of 2.04 times 10 to the negative 13th. Last thing I wanted to mention, this comes up somewhat often, which is, a Le Chatelier's kind of thing in terms of how pH can affect solubility. So remember, when we're looking at these KSP problems, these insoluble substances, we're starting with a solid and we're trying to turn it into ions. So if we want to increase the solubility, we're looking for some change that is going to cause a shift to the left. So again, we need to shift our equilibrium to the left. Sorry, not to the left, to the right. So we want to shift to the right. So the solid is not going to affect our equilibrium, so increasing or decreasing the amount of solid, no shift. But so what we can do is change the aluminum ion concentration of the hydroxide. Now, with these particular problems, we're looking at how the pH can affect things. So obviously, if we were to add a base, if we added base, we would be increasing. We would increase the hydroxide ion concentration. And if we increase something on the right, that would cause a shift to the left. And that would lower our solubility. That'll decrease our solubility. If we shift to the left, we're making more solid. So that's less soluble. But if we were to add an acid, adding an acid is going to remove some hydroxide ions. And so by removing some hydroxide ions, we'll shift to the right. And anytime we shift to the right, that will increase the solubility. And that is everything. That is how KSP and pH relate to each other.